Okay. Okay, so it's a pleasure today to introduce Ignasi, Dr. Ignasi Pérez-Ràfols from the Laboratoire de Paris. Well, it's a very long name, so from Paris. You can, Ignasi, tell the entire name if you want, LPNHE. He's a postdoctoral researcher. He did his PhD thesis in Barcelona under the supervision of Jordi Miral d'Escuder. She's basically working on the study of the gas that is in the intergalactic medium by observing it in absorption lines from background quasars. So studying the Lyman alpha forest and the very beginning of the universe, how the universe cooled down and how the gas was ionized or neutral. And after doing the PhD in Barcelona, he moved to Marseille, to Laboratoire Astrophysics de Marseille. He was there for, I don't know if it was 5 years or something like that.
Just 2.
No, just 2. Oh, it was it sounded to me it was quite a long time. 2 years in Marseille, and after that he moved to Paris, in where you are working now, also working in these studies of the Lyman alpha forest. Ignasi is a very active researcher. He's involved in many projects, leading several working groups in projects like in large surveys like DESI, also inside Euclid and inside many other projects. And he's also a very good developer on different tools to analyze the background quasar radiation and the spectra. So he has developed many tools to analyze in a the details of this spectra in background quasars. So I think this was more or less all. There are many other things I could say about Ignasi. He's participating in many also outreach projects and many other stuff. So if you want to add something, Ignasi, please feel free. And if not, you can just start with your very interesting presentation about cosmology and astrophysics with Lyman alpha forest. Thank you a lot, Ignasi, for accepting to be here with us, and you can start when you want.
Yeah, thanks very much. Just for this nice presentation, just one small correction though. You mentioned Euclid, and I'm not part of Euclid. I am part of WEAVE, Quasars, which I will be covering also a little bit on this talk. So thanks for inviting me here. And as Santi said, I'm going to be talking about cosmology, but also astrophysics with the Lyman alpha forest, right? So just a brief outline. I'm going to be doing this quick introduction on what the sorry, I seem to be having on what the topic is about. So I'm going to be talking about BAO. I'm going to be talking about Lyman alpha. And then I'm going to move to present the current status of BAO as of eBOSS results, using the Lyman alpha, and then I'm going to move to what's going to be next in the future, in the near future now, with DESI and WEAVE, right? Okay, so just to make sure everybody's on the same page, just a few words on the LCDM model. It's very probably known for all of you, but so the idea is that the universe starts with a big bang, very hot, dense gas, and then you start rapid phase of inflation, and then the universe keeps on expanding until we reach some time before, just before the present time, where the mysterious dark energy starts to act and the expansion is accelerated, right? So at the early times, we have like these dark matter particles that we are not 100% sure what they are yet, but that they start to create some small scale fluctuations that then they keep growing as time goes by, right? At some point, dark matter decouples from normal matter, and then normal matter decouples from photons, and then that's what leaves us the cosmic microwave background, right? So this cosmic microwave background have a characteristic scale that has the typical size of these perturbations, right? And then at this point on, gravity keeps on playing, and then this scale can be measured, and it acts as a standard ruler and can be measured throughout the history of the universe at different times using tracers of the matter density, right? So this is useful so that different models, different cosmology models, also alternatives to the lambda CDM, are powerfully constrained by the expansion history. And we can use this standard ruler to measure this expansion history, as we will now see in a minute. The idea is also that the lambda CDM model has its problems. So it's not clear whether what the dark matter or what the dark energy is. We have not been able to measure them. And it's also, there are some tensions between the parameters. So it's natural that there are some alternatives as well to this lambda CDM model, that instead of using dark energy and dark matter, they modify the laws of gravity as we understand them in general relativity to try to explain the same phenomena, right? So this measuring the expansion rate of the universe will help us distinguish between these models. And how do we do that is using this standard rule I was mentioning about, which is called baryon acoustic oscillations, right? So as I mentioned, at the time of the CMB, of the last scattering surface, we have some characteristic scale imprinted on the matter distribution due to the fact that there is this fluctuations of a characteristic size, right? So these we can measure, we cannot see directly from our eyes, but we can measure if we take correlation functions, if we take the power spectrum of the matter distribution, right? So as times goes by, then we can see this imprint on the galaxy map distribution, and then if we have different slices here and here, different times, we can reconstruct the standard, the expansion rate of the universe, right? So before moving on, a few words on the Lyman alpha forest. What is the Lyman alpha forest and what is it important? What are we going to use it for? So the idea is that there are these background sources called quasars, very powerful galaxies, self-similar, so they're quite easy to identify, that emit their light, and the spectra looks something like this plot here on the left. I'm not sure if you can see my cursor, but yeah, here on the left panel. And then we have light. The light starts to travel through the universe toward us, right? So we would be in this end here. And then, of course, as light travels by, then we have the light gets redshifted due to expansion of the universe, and therefore, whenever it crosses a hydrogen cloud, it produces a series of absorptions, right? So as light travels through, the observed line wavelength will always be the Lyman alpha line, so 1215, but then in the spectra, it will appear in a different place, creating what this looks like here in the middle panel, like a very noisy region leftwards of the Lyman alpha peak, right? So this is what we call the Lyman alpha forest. It's not really noise. So of course there is some noise to it, but in general, this is real absorption that allows us to trace the gas between galaxies. And then we're basically measuring the intergalactic medium and the circumgalactic medium. Of course, there are some contaminants. When the line of sight goes close to a galaxy, then sometimes we observe what we call damped Lyman alpha absorbers. Here on the right panel, this is like this very strong absorption with damp wings, giving the name. And also we see absorption from metals in other places of the spectrum. So basically what this means is that for every quasar that we find, we have many, many absorbers along the line of sight, and we can create a detailed map, right? And this allows us to prove the intergalactic medium along a very wide range of distances, of course, only on the line of sight, right? In between the the lines of sight, we don't have information. So this gas is also tracing the large scale structure of dark matter, and then we can use it to measure BAO and then uncover information about cosmology, right? So how do we measure BAO with Lyman forest? Some of you might be familiar with the BAO technique. In general, the most known technique of BAO is the galaxy BAO, by which basically we count how many pairs of galaxies can we find at a given distance, at a given separation, right? And with this, we can measure the 2-point correlation function, and then we construct random catalogs to estimate the covariance matrix, and we can measure, find the BAO measurement, right? So this is like the more mainstream, or the more known maybe BAO technique. But with Lyman alpha forest, even though the technique is named the same, we also measure the 2-point correlation function. We have very different set of systematics. It's like a completely different analysis that just uses the same tool. So the idea here is that we have these clouds here shown in this plot, and then we measure this mean transmission fluctuation field, which we call delta, which is the flux divided by the unobserved continuum and divided also by the mean transmission of the universe, right? And then this delta field is a continuous field, and we take the average of this delta field using a function as a function of distance, right? So we have this function here for a beam in distance in R parallel and R perpendicular A. We have the correlation measured using this formula here. Of course, we can also measure the cross correlation with quasars in the background between different lines of sight. So we would have this thing here and this thing here, and then we would be able to measure the cross correlation, but now we only have one delta to take the average, right? Of course, this allows us to construct the correlation function with respect to a fiducial model, because we need to go from angles and redshift into distances, right? So we choose a fiducial model. Typically, we choose the model from Planck, and then we measure deviations from those models, what basically allow us to measure these alpha parameters, alpha parallel and alpha perpendicular, where if we get a value of 1, we're basically recovering Planck cosmology. But if we don't get a value of 1, we measure deviations, and what we are measuring is this dH over RD and dm over RD. So basically the omega matter and the Hubble constant, right? So now we can go maybe to go through a little bit what this results look like for the Lyman alpha autocorrelation, and this is the eBOSS DR16 analysis, in which I took part, and we can see several things. So in these plots, these 4 plots are a summary of the correlation function, the 3D correlation function, and we have collapsed them in different stripes. So we have here on the top left panel, we have the cross correlation along the line of sight, here intermediate, and then we go further and further away and from the line of sight. And this bottom right is across the perpendicular to the line of sight, right? So we can see here around 100 megaparsecs, we can see clearly a peak here, a peak here. Here in the transverse direction is not so clear, but also in the line of sight direction, we also see this peak. So this peak is the BAO peak that we are measuring. And we have the data points in blue and some simulated spectra that we created to study the systematics in orange, right? On the line of sight, we can also see some other things which allow us to probe information not only on cosmology, but also understand a little bit the quantity of metals that we have in the universe. And as you can see here, there is a secondary peak. This effect is understood, is modeled. As you can see, the model recognizes this secondary peak, and it's produced by metal absorption. So the idea is that when we have absorption in the Lyman alpha forest, sometimes, most of the time, it comes from hydrogen clouds in between the line of sight, but it could also come absorption from other metal species. Of course, if there is other metal species, the clouds that we are detecting will be not at the redshift that we think we are detecting them, right? And therefore, this introduces a secondary correlation function that is offset by the ratio between the wavelength of absorption of the Lyman alpha and the metal species, right? Typically, silicon or carbon. There are like silicon 2, silicon 3, and carbon 4 species that are a little bit in this plot. They are appearing in this plot. Of course, if we went further away in distance, well beyond 200 megaparsec, we would have more species. But then we are not that interested in that regime, as the BAO is usually around 100 megaparsecs, right? So because we know, so this metal absorption, we cannot distinguish from the hydrogen absorption, and therefore the only option is to model it. And that's what we do here. And as you can see, we get a reasonably good fit. Okay, so what does it look like for the quasar cross correlation? You can see here.
First, a question about the previous slide. Sorry for interrupting, but as you said that we can do it. In the top right panel and also in the bottom left, at around 75 megaparsecs, you have a kind of a strange shape, like an oscillation, especially in the one at the top right, that is in the data but not in your models. This is also the same thing you said about the metals, or is another thing?
No, this is what we call in DESI the line not going through the points problem. I'm going to come back to this later in a few slides. Okay, but yeah, this is a known issue, but it doesn't affect the measurement of the BAO, but it's something that we would really like to understand. But I'm going to come back to this in a few minutes. Okay, so yeah, the quasar Lyman alpha cross correlation, as I was saying, it looks something like this. Again, 4 panels close to the line of sight, away from the line of sight, but we can see something very different. And instead of having a BAO peak, we have a BAO dip, right? The reason for this is that the sign of the bias for the Lyman alpha and the quasars are different. So quasars, whenever we have detection, there is a peak in mass, and then in the Lyman alpha, the higher the absorption, the higher the detection. So we can see clearly that the sign is different. So one is tracing like positive matter distribution, and the other is we have more signal when we have less matter, right? So that's why the peak converts into a dip. But you can see that it also measured in the 100 megaparsecs or so, right? So what happens if we combine the two of them? So with the two of them, they offer slightly different directions for the degeneracies, and when we combine them, we further constrain the values of alpha parallel and alpha perpendicular, right? So basically, these are more or less the results that we show here. In blue is the results for SDSS tier 12. In black is SDSS tier 14, and then in yellow, in red is the SDSS tier 16, the most recent results that we have now. And here, this black dot here shows Planck cosmology. As we can see, that we can see some things. Basically, the first thing we can see is that the contours are reduced by about 25%. But then we see also some movement that seems to alleviate the tension between our measurement and Planck's measurement, right? So we did several tests of all the possible systematics that we can think of, and we concluded that this is due to purely statistic changes. So we changed against changes in model, with changes in the software even that we use to reproduce the analysis. And if you want more details about all these tests, I would just point you to this to Wu et al. Paper in 2020, when they are clearly explained in the appendixes. So what does it mean for the expansion of the universe? So here in this plot on the left, we have the growth rate of the matter growth rate and the expansion history. We have placed as a function of redshift, both of them. We have placed all the measurements that we have from BAO, not only from Lyman alpha, but also including the typical the galaxy BAO. We can see here that the constraints on the galaxy are significantly more powerful. Here there is like some, I think it must be quasars, I think, yeah. But then we can see the Lyman alpha are these 2 points here and here. Of course, we still don't have F sigma 8 measurements for the Lyman alpha. This is because we have several degeneracies between some of the parameters. So the extraction of the delta field requires that we do a fit to the entire forest, and therefore this becomes very degenerate with F sigma 8. So we are studying how to measure this, but we are still yet not able to. But in this regime, in the expansion rate of the universe, we have measurements, even though they have a little bit less precision than the galaxy BAO, right? So then why bother if you cannot reach different, like a higher precision or better precision than the galaxies? Well, there are two important things, and the first one is that these are at different redshifts, right? Because they are at different redshifts, it gives us extra information about the shape of the expansion history, right? So this allows us to better understand some of the parameters, right? For example, here down below, we have the open lambda CDM constraints for omega lambda and omega matter. We can see in red the supernovae constraints, in blue the BAO constraints, and in gray the Planck constraints, right? So these BAO constraints in the blue are on the right panel are here represented as well, but are shown also in red here if they are not adding the Lyman alpha forest, right? So if we would not have the Lyman alpha forest, then we would have something that's very much following the supernovae. This means that indeed, because we have a different redshift, because we can measure different things, then we are powerful enough that even if we don't have the same precision as the line of the galaxy BAO, to be really constraining some of the models, right? So this is one of the things that why it's important to also pursue the Lyman alpha BAO. But the other thing is something that we will start to be able to do now in DESI and WEAVE, and it's especially in DESI, and is that the systematics between the BAO Lyman alpha and the galaxy BAO are completely different, right? So now we're going to have many more quasars, and we will be able to apply galaxy clustering techniques to quasars at the same redshift, at a similar redshift, lower redshift, somewhere in between around here, as we do with the Lyman alpha forest. And therefore, this will allow for a perfect set of for a perfect overlap comparison to study the systematic from both analyses and hopefully try to solve some of the tensions that we find with Planck. Right. So, talking about tensions, a few words about the H0 tension. It's probably all of you know about this tension between the SIMB and then supernova measurements, or very local measurements, or I would say maybe distance ladder measurements as well. So basically, if we do BAO and then instead of anchoring on Planck, because let me just go back a few slides. So when here we have this measure, this alpha parallel, alpha perpendicular, if we want to extract H naught and omega matter, we need to figure out this parameter, the sound horizon parameter, RD, right? So usually what we would do is we take the value given by Planck, but then one might ask, okay, so if you're using the parameter from if you're anchoring with Planck, of course you will be more closer to Planck than you would be to the distance ladder measurement. But then we decided, okay, so let's see if this is the origin of the tension. And we decided to anchor in using Big Bang nucleosynthesis measurements. And we found that the tension still exists. So it doesn't seem like the tension would be found in some clear systematic errors in the CMB. We also allowed for a very flexible expansion history. And we also found that the tension still exists. So here we go from the lambda CDM to like very changing the open and then changing the dark matter equation of state, and yeah, we still measure something that's well below the 70 something measured by the distance ladder. So for now, there are still no solutions to the H naught tension, right? So okay, so this is what we have done up till now. But then, of course, you would probably be wondering what we'll be talking about next. And there is the next generation of surveys, DESI, WEAVE, which are starting. We can improve our analysis with the distortion metrics, which I'm going to talk about, related with the question that Santi made before. We have some high column density models that can be improved. We can measure redshift by distortions, but also we can add some other new tracers. So at the beginning of the talk, I told you that there was these damped line alpha absorbers that were acting as contaminants of the line alpha forest. But if we can, we're working on converting these from contaminants to the line alpha forest to useful tracers of the dark matter distribution, right? So a few more words about all of this. So the first thing we can improve is the statistics. So basically we have DESI that has already started observations, right? So here is the current as of DR14. Sorry, I should have updated this plot. But so we have these line alpha measurements, galaxy measurements, and these are the predictions for DESI, right? So we can see that we will have many more points. We will have the expansion history much more detailed. And that is basically because we will have many more objects. And that's simply, just by increasing the statistics, we will be able to split in more redshift bins. We will be able to have better information, right? Of course, you can see here like some interesting things. So we have like this range here is galaxy VO, right? As you can see, the error starts to go up. This is because we start using quasars instead of galaxies to do the galaxy VO correlations, right? And there are less quasars, they're more difficult to detect. So of course, you would have less signal to noise. But then we start using Lyman alpha here. In the Lyman alpha forest, for each quasar, we have many points along the line of sight. This means we get our errors shrink again. And then, of course, as we go to higher and higher redshift, it also quasars become even more sparse, and then the errors increase again, right? The other survey that we'll be measuring with a lot of quasars, a lot of Lyman alpha forest is WEAVE. Just a bit of maybe advertisement here. Since you are from Spanish institutions, you're welcome, you're eligible to join WEAVE. So there are several experiments, and the one I'm talking about here is with quasars. So if you want to join, we can discuss. Just contact me and then I can put we can discuss whether to join or not. I'm serving as deputy lead for WEAVE Quasars, so if you have any questions or that, just feel free to contact me. So what I'm mentioning WEAVE for is this plot here, and this shows the error we estimate for the video measurements compared to the error in eBOSS, and we have DESI here as squares and triangles as WEAVE, and we can see that at very high redshift, WEAVE is going to have slightly better precision, right? So this is not necessarily 100% true, as DESI has already started, but WEAVE was further delayed a few weeks ago due to the volcano in La Palma. So I'm pretty sure you're all aware of that. So then this means that DESI will have greater advance compared to WEAVE, and this means that the constraints might not be as important, but by the end of both surveys, it should be the case. Of course, WEAVE offers also some extra opportunities in the sense that they will have higher resolution that we have in DESI, and this therefore will still be valuable to measure these things. Of course, there are many other things that can be studied in WEAVE, right? Okay, so this is about the future surveys that are starting, but then of course we don't simply want to just say let's go and add more data, but we really want to understand what's going on. We really want to measure improve the analysis. As Santi noted before, there is this line not going through the points here. We checked that the BAO position is not affected so this could be solved, for example, if we add like non-physical broadband terms to just explain the shape of the correlation function. And then in that case, you see the line going clearly through the points, but the BAO position, it remains unchanged. But one quick word is that it remains unchanged with respect to the current precision, right? The exact values are not the same, and they are the same within 0.2 sigma, something like this. Okay, so then this means that as we go further and further, as we improve our precision, maybe at some point this will become important, and before that becomes important and limiting in our measurements, we want to understand this, right? So basically, this effect appears, we believe, due to a number of different things, right? So the first option is the distortion matrix, right? So if we go back to the Quasar Lyman alpha forest plot here, right? Right at the very beginning, you can see that we need to extract here the Lyman alpha delta field, the mean transmission field. And to do that, we need to know what is the unobserved continuum, right? Of course, this is not easy, not trivial to know what the continuum was like before all the absorption. And so we do that by fitting the entire forest, right? So we fit the entire forest in an iterative process that is explained in detail in the paper of Dumas de Barbeau et al. and the latest eBOSS results. But this introduces some extra correlation, some distortion on the correlation function, because now this point here will also have some information. There is this extra correlation that is along the linear side will be imprinted on the 3D, right? So we can model this. This is an effect that depends only on the geometry of the survey, as far as we know, and therefore we can model measuring the distortion matrix. But the modeling might not be perfect, and we really fully need to understand if this is causing some distortion. We are doing in DESI, we are doing extensive analysis on MOX. We are starting to, like, we have seen that there is some small issues there. So we are starting to better understand where this distortion matrix formalism might be starting to break. Right. Of course, there is also some high column density objects like DLAs that I mentioned before that are not detected on our sample, and because they are not detected, they are changing the mean offset, the mean transmission of the universe, therefore impacting the correlation function in a similar way. That's these two effects would be pretty much degenerate, and therefore improving on the modeling of the high column density systems that we cannot observe. This will also be very beneficial, and it might be also impacting these points here in between 50 and 75 megaparsecs, right? So of course, here is one of the key places where WEAVE can be very important, because WEAVE will have higher resolution, and therefore it will be easier to detect these objects, and therefore construct better models that can be then applied to DESI data, to WEAVE data, everywhere a little bit. Okay, so these are like the two main things that we believe are behind this point, but I would like at this point to stress that this is for the time being not affecting our behavior measurements, right? Of course, there are other things we can improve. If we fully understand these two things, we can start measuring redshift space distortion more clearly. We can do in DESI, we're trying to develop new tools to measure Alcock-Paczynski test in Lyman alpha forest, taking into account all these degeneracies between the different modelings, such as the distortion matrix and the high column density systems. So stay tuned for more of this in the near future. Of course, the last thing that we can improve is, and this is what relates us a little bit to the cosmology, the astrophysics part that I mentioned on the title, is that the Lyman alpha is a mixed bag of things. So if we can understand what the Lyman alpha forest is, so sometimes it traces the IgM, sometimes it traces the CGM. So if we could separate these things, then we could understand what's the meaning of bias and beta of the Lyman alpha forest, and therefore gain some astrophysical insights, but also improve our modeling on the correlation function, right? And we are already doing the first steps on understanding this, and this is adding new tracers, right? So we can, as I mentioned before, the Lyman alpha absorbers are absorption, like big absorption features that occurs when the line of sight goes close to a galaxy. But if we look a galaxy here, like in this plot, if we look a galaxy for and then we plot the column density in color coded in this plot, we will see that we have DLAs here at 2 times 10 to the 20s centimeters to the -2, but then we'll see that there is basically few spots where the line of sight can cross, and we can find these damped Lyman alpha absorbers. But then the rest of them are the galaxies is still there. So if the line of sight goes through any other point, we will not be able to detect the DLA, but we will be able to find the galaxy, right? So basically, in the spectra of BOSS, we are developing a technique to find these galaxies in absorption in what we call strong blended Lyman alpha absorbers, right? So the idea is that whenever the line of sight goes through these less dense regions, there is still some absorption that is on small scales clustered, and then produces a series in very high resolution spectra. It produces a series of very high absorption that they are therefore strong, And then they are a resolution of BOSS or DESI or the WEAVE, they're becoming blended. And this allows us to detect these galaxies in absorption, right? So that's why we are calling them strong blended Lyman alpha observers. This is something it's very new. There is just one paper or a couple papers in the literature. The one presenting these objects is Pérez et al. 2014, but they are not called SBLAs there yet. And we are preparing a couple of papers using SDSS DR16 data to show that this is that we can measure and detect them as galaxies, and we can measure their BAO using them. Right. So here are some plots, of course, in preparation. So there might change on when we publish them. Showing the cross correlation of these strong blended Lyman alpha observers with the Lyman alpha forest. Again, because we are seeing galaxies in absorption, but we are seeing galaxies, their bias is positive, Lyman alpha bias is negative, so we see a dip instead of a well, right? And we can see that we can see the BAO not as clearly as with the quasars, because these plots show here are done with DR12, I think. So they're a little bit quite old. We've been working on this project for quite some time now, but yeah. So we can see that we can measure BAO. Probably the fit is not perfect, but we are getting there. And with this, I wanted to just briefly mention before finishing some other science related with the Lyman alpha. So we can measure the 1D power spectrum, right? And this allows us to add some constraints on the neutrino masses, so that are on the opposite end from the particle physics experiments. So therefore, very interesting constraints can be there. This there is some papers on this using BOSS data and maybe I think eBOSS data as well. And there's definitely going to be some papers on this in the near future using DESI data. Then, of course, more on the astrophysics side, we can use the Lyman alpha forest to find these galaxies in absorption, and therefore this means that we can do some population analysis of galaxies, right? These type of galaxies are at very high redshift greater than 2.1, and there are very few galaxies that are observed in that regime. So if we can massively start to detect them now with the Lyman alpha forest, then we can start galaxy formation and evolution. We can do a population analysis of these galaxies at the moment where the star formation rate peaks, right? So this will be a very interesting thing to study in the future, especially after also Euclid starts another surveys like, for example, JPAS as well, or MSE. They will be starting to find these galaxies also in emission, right? In JPAS, there is this called Lyman alpha emitters. In Euclid, we will see more of them with the oxygen 2 emitters, and therefore this is something very interesting that's going to be happening with the galaxy formation and evolution, and the Lyman alpha forest, I believe, will play a key role in detecting these galaxies early. So it's a nice thing to do, and also we can measure a lot of observers in the intergalactic medium with the new experiments. We will be able to measure maybe metal correlations. We will be able to measure DLAs, Lyman limit systems, much more precisely than before, and therefore it's interesting to also look at these other metals. Due to the higher density of quasars, especially on the WEAVE side, we will be able to do some intensity mapping. And then reconstruct the field between the different lines of sight, right? And of course, this is also the whole Lyman alpha forest analysis requires some quasars, the quasars to be correctly detected and correctly identified. And And a lot of things have been going on in that sense. I haven't talked about this today because we didn't have that much time, but I've been developing also some tools to automatically classify quasars. And there are other groups in DESI and WEAVE working with broader dorsal line detection, which are different type of quasars. And this, having this massive amount of quasars, massive number of quasars, will also help us with studying quasar science. And of course, there are many other things that we could do. But then, in the interest of time, I will probably go and leave you with a take-home message. The Lyman alpha forest BA analysis is very mature analysis, but still we are not satisfied that we're pushing to improve it further and further, right? So for now, its constraining power is not as high as BA galaxies, but the redshift is, and this allows us to probe to a different regime on a different, like the expansion history at a different time. And this is also helping constraining different cosmology models, for example, the open lambda CDM, right? BGO combined with big bang nucleosynthesis is also in tension with local H0 measurements, same as if we do BGO plus Planck. So this is telling us something about this maybe pointing towards the direction saying that there are not systematics on the Planck measurements, but again, we are not really sure. There could be something that we are missing, or it could be that BAO is also suffering from such systematics. So it will be very interesting to measure BAO in the near future with DESI and WEAVE. So we'll have more statistics, and if we do have some systematic effects, it will be easier to detect that. Of course, there are different BAO techniques, and the overlap between the different techniques will also help us to convince that we are not having any systematics, right? We can also add other tracers, which will help us understand other galaxies in absorption, which will help us understand the full shape of the correlation function and get some insight of the intergalactic and circumgalactic medium physics at the redshift where the star formation peaks. And with this, I'll leave you here. And if you have any questions, please feel free to ask them. I will be very happy to answer. Thanks.
Thank you, Ignasi. Very interesting presentation. I have a couple of questions, but I will leave first the audience to ask if they have any question. So people in the audience, you can turn on your microphone directly if you have a question. If not, you can just raise your hand and I will let you make the question. No questions for the moment. Okay, so I will start. The first question I have is regarding the massive amount of data for quasars that will be released by Gaia in the next data releases. You know that in Gaia, the spectra is very low resolution for these kind of things. There is anything you can do using Gaia data for quasars in your studies, or it will require to use the instruments like WEAVE to set some observations with WEAVE for the quasars that will be newly identified by Gaia?
Right. So Gaia spectra of quasars are indeed too low resolution, but in WEAVE we are going to use them partly for target selection. So the idea for WEAVE is that we'll be using JPAS data, which offers like 60 colors, like offers the pseudo spectra of quasars or objects in general in 60 filters, and then we will use them to find quasars in photometry and then take spectra from using WEAVE instrument, right? So in the places where we don't have strong JPAS coverage, we will be using, amongst other Gaia quasars, and we'll probably be targeting them but even if that will not be the main target selection, but it's also like that some of them will be observed by WEAVE. Just to maybe complement, even in JPAS, that they have like 60 filters, so 100 angstrom resolution more or less. The resolution is way too low in order to do Lyman alpha forest studies. We would need something like angstrom resolution. So that is what we have in BOSS is angstrom resolution, right? So something, if we have like couple or 3 angstrom resolution, we might get some insight as well. But of course, the higher the better, right? And then, yeah, I would say that minimum to have something useful would be more or less 1 angstrom, and Gaia spectrum are probably not that precise. So they can help us in identifying the quasars, and we will use them for WEAVE quasar program, but we cannot use them directly to measure the Lyman alpha forest.
So another thing related with this, you have WEAVE here in the northern hemisphere. You probably want to have a full coverage of the sky, not just being restricted to a half of the celestial dome. You have any other instrument in the southern hemisphere to complete this analysis of the full sky?
Not for now. Not for now. I think if I recall properly, and this is, yeah, I'm not sure about this, but I think MSE is going to be installed in Hawaii in the near future, and this will also be doing some high redshift experiments. So it's still not clear whether we will have some Lyman alpha experiments on there, but that would probably do that. Help with the coverage on the other side of the hemisphere. Of course, ideally, we would like to have the entire sky coverage. So for video studies, the wider the area, the better, right? But for now, the things that we would have to wait still quite a few years for us to get that. So we have, for now, we will have DESI, which is in North Hemisphere as well, and WEAVE in the North Hemisphere, and SDSS in the North Hemisphere. So for now, unfortunately not.
Okay, thank you, Ignasi. I have another question, but we will try to let people ask also, other people. I don't know if somebody else has a question. If not, I will continue with another one. It's the last one I have, but okay, nobody has any additional question. Okay, so my last question is about something you put it in these last slides. You know very well my interests on galaxy formation and evolution, and also on the CGM. Are you planning to use all these spectra not only for this part of the BAO analysis and more analysis on the Lyman alpha forest, to study CGM in nearby galaxies in a more detail, because you will have a large amount of data with WEAVE, with DESI. So this, of course, it will be a side project that you can also undertake using the same data.
Yeah, of course, definitely. There are many things that you can do that, and we started doing some of these things in BOSS, for example, or in eBOSS as well. So take, for example, stacking techniques. You can, if you find damped Lyman alpha absorbers or strong blended Lyman alpha absorbers and you stack them, you can measure the metal distribution, the metal content of these objects. And we can see, we have already started seeing some very interesting results. For example, if you check a couple of papers I published back in 2018, we show that the damped Lyman alpha absorbers bias depends on the metallicity. It's really correlated with the metallicity. Right, so these more powerful, with extra sets of data, will allow us to even probe deeper into those types of objects. We'll now be able to find Lyman limit systems more clearly. So we would be able to also stack these and find their properties statistically, right? So we can take all this extra science that it's really interesting, and it's more closely related with the IGM and not cosmology, but that's really interesting as well. And the same data set will be very useful for that. Yeah, totally. And then,
sorry.
yeah,
sorry.
of course, then there is not just that, but if you focus on metal absorption will be occurring at different places with different species. And if you analyze that on this data, you will have many absorbers. And then you can use that to analyze. Maybe, so there is also some initial studies on BOSS trying to use the carbon for forest, for example, to measure BAO. So it was not as constraining as the Lyman alpha forest. But again, if we really understand the astrophysics behind, we can improve the modeling, and this improves the results on BAO. So with this huge data set, maybe it will become interesting once again, even if not for cosmology, it will be very interesting for galaxy formation, and especially IGM physics. Yeah, totally.
And just a very last fast question. Do you plan to do some kind of cross-match, for example, with this the CASBA survey or the COS-HALO survey that is being done in the Hubble Space Telescope? They are of course they are observing things that are much closer, around redshift 1, the things that are farther away, but they are obtaining very nice spectra of oxygen 6, carbon 4, magnesium 2, I think it is. I don't know if this can be helpful for your work, probably not for the BAO analysis, but maybe for these and other side projects.
Yeah,
and also,
so
sorry, just a very, and maybe also to test that that the results are consistent between both surveys.
Yeah, definitely testing the results of consistency as consistent. That's definitely an interesting thing to do. But then if we want to compare with these objects, then they are maybe slightly lower redshift. The redshift is maybe too low for our typical data, right? So I would say maybe not for the Lyman alpha, because Lyman alpha is redshift 2.1 onwards, and if these objects are like around redshift 1, this is too far away to have any correlation, that residual correlation. But other metal lines, for example, if you check magnesium 2 observers, that could be more or less in the same regime, and that there could be some statistical interest, or some interest also on doing these correlations between these objects. Yeah, definitely. And of course, you can also do some other correlations with the Lyman alpha forest, and for example, the emission, Lyman alpha emission found in JPAS, for example, in not source by source, but like a broad emission, like the background emission. So that other things like this are also interesting. So if we have like data that is photometrically, it's not like very broadband photometry, we can also try and correlate with that, and to get some insights as well. Yeah.
Great, thank you, Ignasi. So I will leave the last chance to ask something to Ignasi, to the audience. If you want to ask something, please proceed. If not, we will thank again Ignasi, and we will leave the seminar here. So somebody else has a question for Ignasi? No? Well, so thanks again, Ignasi, for coming, for accepting our invitation to the IPARCOS seminars. Hope to see you soon, and maybe to have you in person in the UCM. And I invite everybody to come in to the IPARCOS seminars next week. The day is the 13th of October. It's Wednesday this time. That we will have Carlos de Burgo from the INAOE in Mexico. So you are invited to come to the IPARCOS seminar next Wednesday. Thank you again, Ignasi, and see you soon.
Thanks. Bye.
Bye.